So I'll just get right to it. I don't have time. I have way too many slides. And you can read the title whenever you feel like. So let's go to the motivations. In my team, we have like a 167 core processor. And one of the things they have is that it's GALs, so it's globally asynchronous, locally synchronous. And each one is communicated through FIFOs. This is very important to understand that each of the processors are very simple. So, you might think after watching my talk or reading my paper, this is ridiculous. But the thing about it is that I'm trying to make a new way of thinking instead of saying this is going to be practical. Maybe some of it will not be. But let's see. So I'm trying to first do the DBFS. That's the main point, is to try to find an optimal algorithm. How will we do that so far? So far, what I've seen is that we have a lot of control system algorithms. That's true. There's a lot of papers on that already. But what I thought about them was that it was like sending a nuke to destroy a building. This is like overkill, maybe, because especially for our architecture where each core is already low power, adding any of those techniques that I read wouldn't have made any sense. It's better not to do DBFS then. So let's see if we can use circuits to model the control system and then go from there to make the algorithm. So here's a simple case where we have two cores talking to each other, a producer and consumer, going through a FIFO. And what I've said here is that, okay, it's a producer-consumer application, and then I'm going to do a little analogy here using physics. We say charge is a sample. And then next, we have a current, samples per second, which is our data rate. Then we say conductance is cycles per second. Okay, just believe me on this. And then next we go, okay, voltage, samples per cycle. And then how I get samples per cycle, I just use CPI times IC, basic computer architecture, and then validate this. Ohm's law. I is V times G, conductance, right? The data rate, samples per cycle times cycles per second, all matches out. Now, I want capacitance. What's a FIFO? What's the FIFO? FIFO capacitance makes sense, right? FIFO stores charge. We're storing charge right here. So let's validate this one. Q over V, it's cycles. So basically, any difference between the voltage here and the voltage there, creating a current, and the resistor values, which is our frequency, okay, basically conductance, will cause a difference to appear here. And that difference is something we want to get rid of. This would produce the right number of data rates that this would consume. So the producer and consumer would have the same thing. We want to have this to go to 0, which is my next slide. But anyway, the time here shows RC, right? Capacitance over conductance. I get seconds. So seconds in my fake model world is the same as seconds in my real world. So that's beautiful. Let's move on. So anyway, that's what I basically said. I want this to go to 0. This is exactly what I want. Because if FIFO was a positive number, that means that FIFO is full. If it was negative, that means it's empty. All right, what does that mean? If it actually has that value, that means this FIFO value divided by that core, either one of these, depending on if it's full or empty, basically means that the percentage of this time, this core would be not working at all. It would be stalling. I clock gate, or I could, that's basically what I would probably do. Power gate or clock gate this guy, or power gate or clock gate this guy, depending on this percentage number. So the amount of time we have percentage is what we want. But we want it to go to 0 because we don't want any of these to stall. We want to have the optimal energy point, right? Because I could always save power by just stalling these guys and power gating or clock gating, as the case may be. But anyway, I'm going to derive my continuous time model. And I'm making a big assumption here. What I'm making the assumption is that my period of control, basically every time I do an action on this, basically saying I want to change my resistor values or I want to change my voltage, whatever that possibly entails in the underlying architecture, it has to be much greater than the actual frequency that's running the cycle. So I can basically make the assumption it's continuous because T is going basically much larger than the actual cycles going in there. So that was one complaint about my paper, is continuous time model. It's ridiculous. But guess what? When we do current, we're already modeling like discrete charges as continuous time. I mean, physics is already saying it's discrete, right? Anyway, let's go here. Varying the conductance. So I want to make my problem simple, because if I went back here and try to change this conductance value by changing its frequency to any point, that's like a nice DC-DC converter. I can do anything I want, but that problem makes it nonlinear, like it's really crazy. So let's simplify the nonlinearity a little bit and make it choose between two values, which is like, you know, we have VDD high, VDD low type of systems, so it's possible. And I got rid of some of the producer. I say the producer is coming from an ADC, so it's giving me data values that's at a constant rate. So then I took that, made a MATLAB model, so I did this in like an hour, and then I was like, okay, let's do this, because I had to get the paper in like 6 hours, so let's do this. So let's make this run, and then boom, 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 magic, right? So another criticism, this was magic. Yeah, it is magic, because after I got down to it, it took several hours to get my end result to this optimal point. So I took a nap, woke up, said like, whew, hey, it worked. So the point here is that we have two cases, okay? So one is high, one is low. I set one to be 1 voltage, 1 frequency. I set another one to be a voltage frequency. So the ideal case will get me to this point here in the purple, or whatever color you might think it is if you're colorblind. So 72.22%, 27.78%, okay? But it gets to this. Well, you have to remember the chip is not perfect. I mean, we're not using PLLs to get our clocks here. This thing is running on a ringed oscillator, so this might not be exactly true. That's why I'm getting such a weird number. But hey, it was close to the optimal, and this is what the end result was between the two values, because if it was at here, 15.6, that's pretty close to the ideal case, 12 milliwatts. Anyway, so it took several hours. So that's one thing I didn't mention, right? But there's another problem here. There's a big problem. I made a very big assumption. I assumed that when this went negative, this thing would like not inject more charge, because when you go negative, this minus this means more current. Systems don't do that, right? If the FIFO is empty, it doesn't mean I'm starting to put more work into the FIFO. I made a bad mistake. Well, that's what happens when you do things in 6 hours. But anyway, okay, went back. This is not in my paper, right? So then I had to correct myself here. That's probably why, one of the reasons why things like didn't work exactly as the MATLAB model did. And there's other reasons too, because, yeah. So you got this, negative, what do you want? Oh, it goes higher? That's not true, and this is not true. So we have to add current limiters. All right, what do? Hey, you know, this something looks similar to something else. It looks like a MOSFET, right? Because MOSFETs, you can resistor, and in another region, you're a limiter. So I took that and I said, hey, well, you know, you can just do the equations and you can get what you want, but there's a little like, in real life, you know, MOSFETs are not like exactly what the linearity you want it to be, but you can always change your SPICE model and get what you want. All right. So here's the new world. This basically, I'm changing this to 2 sets of MOSFETs, and you know, if you do power gating, you use 2 sets of MOSFETs to do power gating anyway. So this is quite good because, you know, the analogy matches. Just like on my other analogy where seconds in the real world is seconds in the fake world, this is like transistors in the real world, transistors in the fake world. Perfect. This is very beautiful. So now I got this going, and you know, you can just think about it for yourself. I just make a controller, control 2 power gates, exactly like I do control real power gates. Awesome. All right. What's the other argument, right? It wasn't practical. Because how could I possibly do that and assume things? I don't have cache miss? What? What happens when I have like uncertainty in the OS? All right, those arguments were valid. Fine. But I'm just trying to introduce a new idea. Okay, so I took Thomas Who's algorithm. I just did like 2 days like thinking about this. So let's see if this guy's around here. So I'm trying to address his problems. Yeah, you can read any Hennessy Patterson. You can find this stuff. This is basically a block diagram. Right? So can I turn this into resistors and capacitors? Is it possible? Well, I don't know. I just did this. All right, I'm not a mixed signal designer. I just started like whacking it out like this. So let's see, bias points, put some comparators, this, that. Doing it more here. And the interesting thing is, if you look at the inductors, it's basically modeling the pipeline. So when you first have a pipeline that's empty, right, you're putting instructions through it, it takes a while to get throughput going. Inductors do that. Because you put it in inductors don't like current changing. So only at the end, current starts like changing, it's like against the tide. So if I just like let go and don't put like new instructions in the pipeline, it's still sending out throughput for a while, right? You can model that with inductors. Hey, why not? So I have the perfect model here. RLC, all accounted for. Okay, conclusions. Well, I give you a circuit model, you get the control system, and the thing I'm trying to emphasize is that when you do control theory, you get nice stuff. You get like phase response, frequency response. What do those mean for computer architects? I don't know, but it definitely helps you think about things rather than like I'm just going, oh, I think an L2 should be this big or that big and run a bunch of simulations. Here at least I can think with design. Analog people don't get paid to be like, hey, do this, whatever, come back to me later and give me something with simulations. No, they think about what they're doing and they get paid lots of money. So how do we do this? This way we can make things more holistic, right? Going from top down, bottom up, whatever you want to say, everything matches. And you know what other thing is like, okay, there's another presentation I went to, they said like don't use a wrench, like a crescent wrench for any problem you want. But right now we're using hammers, saws, I guess screwdrivers, could be anything. We're not even having common wrenches, right, to fix a plane. So the guy said like a guy would get fired if he didn't use the right type of wrench to screw in the bolts for the plane because the plane blew up, they get sued. But anyway, the point is, we don't even have common tools. Everything is like different. So maybe if we had just use SPICE for top down, bottom down, up down, whatever, side to side, we can get something. So here's acknowledgments, people who funded us, and thanks for your time. I got plenty of time to ask questions. All right, cool.